All right. So if you have been on Blackboard, you may have seen that I added some stuff last night. Up to this point, I would like to think that you're to the point that you could design your basic trunk layout based on last week's class. If you haven't watched that, it is available on Blackboard. It's on, see, is it trunk sizing? Yeah. Yeah, trunk sizing, module 12, trunk sizing. There's a lecture on there, duct design and load correction lecture. And then there is an assignment with that. So if you haven't done that, I mean, it's actually pretty easy. You just fill in the blanks. But I'll go ahead and, if you need a little extra time to get that in, that's fine. But that was assigned last time. So if you haven't done that, try to get that. I only had 3 as of last night. So I figured there may have been something going on with that you haven't got it yet.
Did you happen to look at that stuff?
Having to look at what stuff?
That assignment.
Like what you all turned in?
Yeah.
I'm trying to think if I saw yours. I'm trying to think whose I had. I know I had Corey and Garrett. You might have been the third one. I can't remember. Why, did you have a question about it?
No, I just was. Yeah, I was going to see if I did it right. So, but we can do that later.
Gotcha. Okay. Well, and this may help you. I mean, what we kind of start talking about today, or maybe even my next class. Oh, my mother is calling me, but she'll have to wait. Okay. All right. So here we go. Trunk sizing. I'm going to go back up to friction rate, module 10, calculating friction rate. And I've downloaded a bunch of stuff. So I'm going to see if I can share this screen so that you can see where I'm getting this from. Screen 2. All right. So you all should be able to see a sheet that says that's Blackboard. Can you see that?
Yes.
Okay. I've lost you all. There you are. Okay. You should be able to see module 10. I just put some different stuff in here, mainly specs that we're going to pull from. So can you all see that? Everybody good? All right.
Yes.
Okay. So the first thing we got to start with, when you all started looking through calculating your friction rate, did you watch that video calculating friction rate in TEL that I had posted last week, or well, it was a few weeks ago? This video right here, can you all see that? Okay, so this guy,
yeah, it took him 45 daggone minutes to get to anything that we actually needed to know.
Well, it was only 22 minutes long, so
I must have watched it on slow then, or it just felt incredibly slow.
Well, so he actually does a really good job of going through the process. I mean, yeah, you do got to navigate through it, but it's okay. You got to navigate through me too, is what it is. So it's, for me, I'm still trying to navigate the right path to get where I need to get to. So our main goal is to get to a friction rate that we're going to plug into our duculator, into our duct slide. So last time we used 0.1 and we just said, it's kind of, the industry rule of thumb, and they'll just say, well, just use 0.1. And the reason why I think they say use 0.1 is because, as you'll see, it takes a little bit of work to do it, to actually calculate one. And so we want to calculate one on our system as close as we can. I'm not going to go crazy through it, but you can really, fall into the hole if you want on doing this. If you had some sort of crazy duct design or something, this could get pretty complex, but even in a very simple fashion, it's pretty complex. So I'm going to pull up a couple of things that we're going to need to use. So the first thing we're going to need to find, and I'm going to I need to have that guy available here because I got to use him as my guide. Because I got to go back to what he's saying and make sure I'm doing it right. So the first thing we need to find is we need to be able to find available static pressure or external static pressure. Sorry. So have you all even messed with this at all to the point that you could kind of help me walk through this? Because I got a feeling some of y'all have got notes. Like Chris probably has notes.
No, not.
No. Okay.
Not really.
I had kind of said if you wanted to start looking through it, but I know there was some missing holes that I hadn't filled in. So anybody else got any kind of notes that you picked up through that video? Because he does do a pretty good job of walking you through it, even though you do got to sort through. Can you see him? Okay, so here's this, and you probably won't be able to hear him, but I'm going to use this as a guide. I'm kind of going to walk through what he's talking about. So the first thing you're going to need is you're going to need some equipment specs. Well, you're going to need to know your room by room loads. So you can get this from whatever heat load calculation that you used. So in our case, we used a few different ways. We used RightSoft, we used speed sheets, and we also used that Cool Calc. And we came up with 3 different, basic heat loads that we kind of laid out. I'm pulling this from the RightSoft that I did last week, that I walked through in class, the room by room. But if you look at your speed sheets, you should be able to get this as well. So in your speed sheets, it should give you room by room loads when you go to that breakdown, and then it should also convert those room by room loads to CFMs, which is the amount of air that you're actually going to need for that room. He does in this video, he does kind of go into calculating, like if you knew BTUs, it's toward the end here. Let's see. If you knew BTUs, but you didn't know, it didn't give you the static or the CFMs per room. Let's see here. Can you see this formula? Required airflow for a room is found by using the following formula. Chris, can you see that?
Yes.
Okay, since you're unmuted, I'll ask you. So he's saying you could take this and say that airflow equals the heat load from the room divided by the total heat load times the design CFM. And he runs kind of through an example of that. So the design CFM is the CFM for the whole house. The total heat load would be the total, 36,000 BTUs or whatever you have. And then the heat load from the room. So you're basically taking a fraction of that. And then if you run that formula, it should give you CFMs. Now, the thing I don't know, and I would like to see this broke down a different way, is if that formula, because if you do rule or order of operations, it's going to do heat load divided by total heat load times CFM. Or if it is heat load divided by, and then those should be parentheses. So I'm not sure on that. But either way, our program does this. So as long as you have a program that calculates your CFMs, you should be okay. If you didn't, like if you were using like an old fashioned, like that hand sheet that we did, and it just said, this is your load or whatever, and you just came up with a BTU, and then from that you could calculate design or your room by room CFM. So I'm not gonna spend a lot of time on it, but that's kind of what it's based on. So, all right, so let me go back. So you're going to need some information on your equipment that you're going to put in. And you could run some examples and say, okay, what if I did this system versus that system? In this case, I just picked some random units for us to fool with. And then I've also got this page here that is a friction rate worksheet that I found online. I just typed in friction rate worksheet and it popped up, and it's actually pretty slick because it actually lets you fill it in. So if you go to your manual D book, this sheet is all throughout this book. They use it over and over and over and over. I don't know, there's probably a blank one in here, like a template, but then like for all these examples, they use it. And so it says friction rate worksheet, like on page 55 of your manual D book, there's one example. And so I'm actually gonna see. I may end up just pulling from that one. Yeah, let's just go to that one. So page 55 in your manual D book, if you have it, there's a duct system on page 54, and they calculate a total equivalent length or effective length or whatever. And then on the next page, on page 55, they go through this pressure sheet, this friction rate worksheet. So it's actually a really slick thing because it walks you through all the things you need, gives you your formulas and the whole deal. So that kind of gives you a starting point. So the first thing you'll need to know, according to that sheet, is manufacturer's blower data, and that can be found in the manuals. So let me get back out of this. So I've got a bunch of stuff in this folder. All right, so I just picked some rude stuff. I didn't pull out an air handler because I think this job calls for a furnace, if I remember right. But I did pull out an air handler coil. So there's two different things you're going to have to find in these manuals or in the spec sheets on these units. And sometimes all of this may not be in the installation manual. You may have to actually go to a spec sheet, and the spec sheet is going to give you some of your duct pressure losses. And so I've just said we're going to use a 95% furnace with a coil, an AC coil on top of it. But then I also went through and just pulled an air handler coil, for example. So I'm going to pull up this furnace because the first thing I need to know is manufacturer's blower data, and that's going to come in the air handler or furnace manual. That's going to be where your blower is. And so I'm just going to download this file. And if you all can't see, I've got this manual pulled up, this Rude Achiever Series furnace manual. So if you can't see that, let me know. If you're following along on Blackboard, all this stuff is in that folder. So you can pull this up now or you can pull it up later, whatever. All right, so I'm going to be looking for blower data. And if you go to your table of contents, usually it's right in there. It tells you where to go. So this says it's in page 7. This is a pretty small manual. This is a spec sheet, I think, versus this is not a full installation manual. So this has a lot of specifics. And so this gives you all the information on these furnaces. So whatever version we're pulling up. So what was our heating load was about 40,000, 45,000, something like that, right? 50,000 maybe at the most, I think is what we had. So I'm probably going to end up pulling from this R95 PA060, which is 60,000 BTU furnace. I have a 40,000, but that's right on the border of being enough. So I'm going to say I'm probably going to end up on this 60,000 furnace. And so I'm going to go on. Do I?
Are we supposed to oversize a blower? Is that?
Well, you can adjust. So a lot of these units will come with a blower that'll do multiple tonnages. So if you'll notice right here, like this specific furnace only has 2 blower options with it. It has if you look at this model number identification, this number right here, airflow, is either 3 or 5. So it's up to 3 tons or up to 2 or up to 5 tons. And then you go in and actually set your speeds. And so if it's a 90,000 BTU furnace or whatever, then you set it for your AC match and your heating output match. So you kind of got to, you can make this furnace work in a lot of different places. So you're not going to get a 3.5 ton furnace blower. You're going to move the speeds of that blower to get what you want. So they're a little more generic than what you'd think, maybe. All right, so I'm going to go down here. So I'm looking for blower performance data. So this is on page 7 of this manual. All right, so we said R95PA060. All right, so that's our 60,000 BTU right here. There's my alarm. So I gotta call in here in a minute. If you haven't been on here very long, I've got to call in and try to schedule a doctor's appointment for my kid here at 8:30, so I'll mute you all. But your R95 PA, and then I'm going to go over here. Now, on that video, so how many cubic feet per minute of air do I need for cooling per ton? Do you remember kind of the general rule?
Said
Do what?
400.
400.
400.
Yeah, so it's 400 is kind of just standard. And then if you're doing dehumidification, like heavy dehumidification, you might do it a little lower at 350. So 400 is pretty standard across the board. So our cooling load was what, about 2 ton, give or take? Am I right?
I think so.
I think
Yeah.
so. I think that's what
Yeah.
we ended up with. And our airflow, if I go to my little sheet here, I'd have to go back to the main sheet to see what. Does anybody have it pulled up real handy where what your total airflow? I'd have to add these up. Total required airflow was
Yeah, it was 1,099.
1,099. Okay, so that's what we need. So that number. So I'm going to try to find something close to a 0.5 static, because that tends to be kind of the guideline that most of these videos that I've watched use. So I'm going to try to find something that's close to what I'm looking for. So I've got a couple of options. I've got 1010 at a 0.5. So that's real close. 10, what do you say, 1090? At a 0.4 static, I'm about 1060. So let's just say we're going to use a 0.5 static because that seems to be where most of them land on this. And that gives me 1,000 CFMs on medium high speed. So I'm going to select on this blower, I'm going to select medium high to get the right amount of airflow that I need. So I just have to go into the manual when I set this unit up and make sure that I set it to the right speed. So even though the system may only be 2 ton, because our house is built pretty well, the cooling load is 24,000 BTUs, but I need a little bit more air to actually deliver that because of, the size of the house. So the better built your house is, you may have to have, like, you could have a humongous house. Like I know where there's a huge house that only had like 2 or 3 tons of cooling required per floor, but they had to have like a 5-ton blower to move it. That's pretty unique, but just keep in mind that those things aren't necessarily tied together, but usually they kind of are. And so in this case, it said we needed a little bit more airflow. We needed about 2.5 tons worth of airflow. And so, we're going to use that 0.5 at 1010. All right. So I'm going to mute off here just for a second, and I'm going to let you all kind of talk amongst yourselves. See if I can do a breakout room. All right, so here's what I want you all to work on. The next thing you're going to want to find is you're going to try to work through the next part of this sheet, which is component pressure losses. You're going to pull that information. Let me see if I can find this. I'll see if I can pull it up so you can see it. From the coil specs. So one of the things you got to look for is your refrigerant coil. How much pressure loss through this particular coil? So you could use a general number, but most of this information is actually in your spec sheets. So I'm going to use a coil on top of this AC unit, and I'm going to upload this file. Uh-oh. There we go. All right, so I'm going to let you look at this. Like I said, I've got to step out and just make a quick call. As soon as I can get through, I'll be right back. Let me see if I can find the right page. Coil specs right here. Okay, so let me zoom this in. So we're going to be using a 2-ton coil, which is one of these, either the 2414 or the 2417, and that's probably with that 17 and 14. So we're going to use
cabinet on that furnace.
Yeah. 17-inch cabinet. So I'm going to use this 2417 and going to use this coil right here. So this gives me the pressure losses, static pressure drop through a wet coil, your airflow right here. So this coil is going to have a pressure drop. Let's see, design CFM 600,000. Make sure I'm looking at this right. So 1,000 CFMs. Point 0.38.
Would it be 1,000 CFM, or would it be design CFM, or actual required? Because 1,000
that's
would
a
be
good question.
1,100 and would bump it up to the next block.
Okay. Yeah, that's true. So that puts it at a 0.45. That's pretty aggressive, really. So if you're at 800, if we were going back to the whole like 400 CFM per ton, you're at 0.23. So trying to push 1,100 CFM through that coil may end up being a problem, and that's what this is going to tell us. So that's your 0.45. All right. So let's just use that as your coil pressure loss. So you would write in 0.45. So if I pull up this file, where's it at? Not there. Friction rate worksheet right here. All right, so I'll link this on Blackboard as well. So your total external static pressure is 0.5. Your CFM is 1,090. Let's say 11. Let's just say 1,000 for argument's sake. Coil 0.45. Is that what it was?
No, 3.8 if you're going to use 1,000.
It's 3.8. 0.38.
If you were going to use 1,000.
And all right, so what I want you all to look at while I'm stepping off here for just a second, you can talk amongst yourselves, unmute or whatever, and you can say Adam's crazy and doesn't know what he's talking about, and I'm so confused. That's fine, but I want you all to go online if you can, if you have access to pull up another tab. You can pull up the information that I've put on Blackboard about the filters. So that's one of the things we're going to have to calculate, and you might want to look at a couple different options. So the two options that I'm using are an Aprilaire filter and then a Filtrete like high capacity pleated filter, like a 1-inch filter. And so I've got both of those on Blackboard. If somebody has the ability to kind of look through those two files, maybe on a separate screen or something, pull those up and see if you can get some information from those two tables. Do a little independent research if you want. So I'm just using Aprilaire. I forget maybe a 210, I think, is the size I'll need. So see if you can find friction rate for pressure loss for that, and then a pressure loss for like one of those super duper Filtrete, awesome $30 1-inch filters that you get at the store. So we kind of want to run a comparison just to see if there's a big difference. And so when I come right back, I'll let you know. Let's see. I'll let you know what I came up with. So
where was that at, Adam?
It's on Blackboard. It's in that same module. It's in that friction rate module. So I'm going to mute and jump off here for just a second, and you all can just kind of talk amongst yourselves. Remember, you are being recorded, so I can go back and listen to all this, see what you say about me.
Are we just doing a basic filter?
if you look, I don't know, he's got two pulled up here.
I'm looking at the April Air, and so there's the unit, and then there's upgraded. Well, that's replacement media. And then there's the upgraded MERV 13.
I see that.
I just say basic. Inches water column at point CFM.
So would it be 0.04 at 6? Well,
It'll be 0.08 at 1,000, right?
yep. So 0.08.
Yeah.
And where does that information go on this worksheet?
So on the worksheet, it'll go into the crap. I lost my team.
The high
Right.
or medium efficiency filter?
It'd be high or mid efficiency. Yeah, it'd be the high or mid efficiency filter.
And where did you all see that information on the spec sheet?
So on the spec sheet, just going off the basic model.
Oh, I see it.
Model 2210.08 at 1,000 CFM.
I got you. I see it. Nice.
So then,
Grills, outlet.
If I'm reading the chart right, I think the 1-inch MERV 13 has a initial resistance at 1,000 CFM of around 0.2 for a 1-inch.
These are okay.
All right, got it figured out?
Nope.
Okay.
Yeah, we do.
You do? Okay, what'd you come up with?
Well, on the April Air.
Let me pull this up so everybody can see what I'm talking about. So this is listed as filter specs. And I got a couple of different files. One is an April Air. And then the other one is a MERV 13 pleated. So this is another one of those examples, guys, that like, this isn't like how to put together your kid's bicycle. Like this stuff is like, like full of all this specific information that you may end up needing. Same way as installation manuals. So like right here, I got all the information I should need. So walk me through what you did.
So we just did the basic model, the 2210, and found it has a resistance of 0.08 at 1,000 CFM.
Okay.
Because that's our.
Okay. So 0.08. So just,
yeah.
If you're, as far as I'm concerned, you can write in your book. I mean, it's your book. 0.08 or, hold on a second.
Is that what you would agree?
Yes.
Okay. Yeah. Good. We come to the right conclusion.
Hold on just a second. Let me go check on my kid. He's hollered.
Mm-hmm.
Never had to say that during a class. Unless you're throwing up, don't bother me. All right, so 0.08 at 1,000. Now let's go to this other file. MERV 13. Let's see. Now, this one doesn't give me necessarily the specifics that I'm looking for, but I just use this as, I wanted this chart more than anything. I wanted to show you this. So check this out. The thicker your filter is, you'd think that it's worse, but it's actually better. So pleated filters, if you do 1-inch filters, which are kind of these standard filters that that most systems come with, 1-inch wide, your static is going to go way up because you've got, the more aggressive that filter is, there's less surface area for it to actually work through. And so it's not the best at all to put in a really aggressive filter in a 1-inch cabinet. If you go to a 2-inch, it does help it some, and then going to a 4-inch helps it even more. I want to see if I can show you something real quick. I forgot to pull this up, but I do want to show you this if I can find it. So Aprilaire. Let's see if I can find it this way. There's a video. He says. Well, somebody's unmuted here that, yeah, jumping in and out. Okay. There is a demo here, but I hadn't pulled it up, but what is that? Did y'all hear that? Oh, it's pulling from, okay. Never mind. I was like, I'm hearing something, but it was, I guess when I scroll over this, it's listening to the sound. There is a video somewhere. I would have to find it, but it's basically like they take one of these filters, set it on a roof, and uncut all the frame from it, and then just drop the filter material. And like a standard 1-inch pleated filter has very little room to move. It's basically just little triangles, but I mean, they're only a 1-inch tall. And then they take a 4-inch pleated filter. So if you see like this one right here. See if she no, she doesn't. But anyway, it's basically a accordion style filter. And you've got a lot more surface area. So when you increase your surface area, you decrease your static pressure. If you had to use a 1-inch filter for some reason, let's just say you didn't have any other way around it, you could, I mean, I would honestly go with a less aggressive filter because those others are really aggressive. And I can't tell you how many service calls I've been on that they have units that are freezing up, or in the wintertime, their heat pumps are going out on high pressure, or their furnace is kicking out on a high limit, and you pull the filter out and it doesn't even really look that dirty.
Purple filtrite.
Do what?
Purple filtrites.
Purple filtrite. What's that mean?
I don't know what MERV the purples are, but it's
so total... you run into that with them?
Oh yeah.
Okay, let me see here. I've got the filtrites on here. That's what I was looking for, and I pulled up the wrong thing. Filter specs. Let's see if this is it. Here we go. Purple filtrites, and you can even go more than that. So look at your pressure drops across these. Now note, ours was running 0.08 at 1,000. Now this one doesn't go as specific. It doesn't give you airflow and all that stuff, but just look at where you're starting. So if you go over here and get one of these ultra fine particle reduction, 0.26, like that's almost as much as our coil has, our whole air conditioning coil. And that's when it's clean. So then you add dirt to this thing, and now you're just stopping this thing up like crazy. And so people buy these because it says allergen on it. Here you go. Here's your ultra allergen purple filtrate that Brendan's talking about. And they buy these things. They pay, $40 for this filter, whatever it is. Well, this one's $16.49. But, they pay 30 some bucks for a 2-pack of these filters. You got to change them every month, if not more. But most people, do they change their filters every month? No.
3 months.
Yeah, 3 months. And it just won't hold up. It gets stopped up with stuff because it catches everything. Like, they're good. They're good at doing what they do, but they're too good because they stop everything, including the air. So these are harder on your motors. You don't get the design airflow that you're supposed to be getting. So now your air conditioner is starving for air. So that causes all the problems that can cause. And then over time, this causes your motor to have to work harder, which causes early failure in blower motors and stuff like that. So I hate good 1-inch filters. Just hate them because I can't tell you how many times I've took them and threw them in the trash and they're like, that's a brand new filter. And I'm like, it's junk. Because you pull it out and the system just goes, and it just breathes. And like, I can think of one right offhand that is actually close to me that looked like it was completely clean. Pulled it out, hit it on the floor, hit it on the ground, out on the deck, and like a bunch of really fine white dust came out of it. And it looked like sheetrock dust, but they hadn't been sheetrocking. And he was like, because my pressures were just tanking. It was summertime. And so I was running, borderline freezing, that kind of stuff. That was why he had me down. And I said, well, what about that filter? And he said, I just changed it a couple weeks ago. I pulled it off. Everything came up where it was supposed to be. And he was like, can't be that filter. I'm like, it is. Watch. When I put it back on, starts freezing up again. I said, give me a new one. Put a new one on, and it was like right on the border. And just any dirt that it picked up, it was putting it over. So I hate them. If you had to have one for some reason, one thing you can do is you can increase the surface area. So you may see something like, and I don't have an example of it pulled up, but I have seen people that'll put in even like 4-inch, probably more like 4-inch cabinets, but they'll increase the surface area across that coil to where they can put a bigger filter or a wider filter than their ductwork. And so they may make like their duct may come down and then they come out with like a diamond and then they go back in. And so that gives it this expansion room. So it has room to work through it without forcing it all through this little tiny hole. So the less square inches you have, it's going to increase your pressure because you're trying to move the same amount of air through a smaller space. The more restriction you have, it's the same thing. So I use these April Airs like they're about a $200 upgrade, but I just include it with every system I put in because the Roods that I put in don't have a filter slot in them, and honestly, I'm kind of glad that they don't. A lot of your Goodmans will have a filter slot. A lot of other brands may have one too, and a 1-inch filter will fit in it. And if a 1-inch filter will fit in it, then people's going to put a 1-inch filter in it. And the bad thing with those is most of the time they're an odd size. So they're like 17 by 23 or something and 17 by 21. You can't buy that at Lowe's. You can't buy that at Walmart. You got to order an odd size filter. They only come in, 20 by 25 or 20 by 20, 16 by 16. And so what I've seen a lot of times is they'll go out and they'll buy a 16 by 25 filter and they'll stick it in this 17 by 20 slot, 23 slot. They'll leave a bunch sticking out, which is fine. But then they've got a 16-inch filter and a 17-inch hole. Air goes right around it, and then their coil's filthy. So I hate 1-inch filters because they just cause so many problems. And
so how
I got to read
one of the Airs?
Do what?
So how would you add one of these April Airs to an existing unit?
Most of the time, if you got room, you can do it. I've added them to several. Obviously it depends on the installation, like how much room you have. But like if you have a furnace that, maybe it's standing up in a basement and you've got a furnace and then over beside it, you got your return duct coming down. If you got space in between those, you could put it right in between, or you could put it in the return duct, or you could raise the air handler and set it underneath of it. Obviously, that's going to take a little more work and it may not be quite as feasible. But I've done a couple here lately to where I just go in and cut out their duct, slide in one in its place. And so air cleanliness is a big thing for people right now. And that's a, yeah, you can get purifiers and stuff like that, but sometimes people don't want to invest that much. But a good filter, like you can never go wrong with a good filter. And most of these April airs have a 6 month to 1 year replacement. So this is really good for people who have to crawl under their house to change their filter, and they have to do it every month. They don't do that. So if you could say, hey, what if I could just make you, have to go change it every 6 months? Then, give them one of those filters, go in there and change it, every 6 months, go change it out every, at the beginning of cooling and the beginning of heating season, go change your filter. So they do a great job. They do catch a lot, but because they have so much surface area across those pleated surfaces, if you take, a set of triangles that are just, 4 inches tall and you spread that out, you got all kinds of surface area. I'm gonna look for one this time. April Air.
I put in a lot of Air Rangers.
What are they?
EACs. They're
electronic. Okay, so they're electronic air cleaners. Yeah, that's a whole other category. Are they 1 inch?
Yeah, they're 1 inch, but they're really fine. Like there's a lot of air. It's easy for air to move through them. It's just statically charged. 24 volts.
So they're not really a filter. Do you use them with a filter, or do they have a filter with them built in?
They use filter pads.
Do what?
That the static charges the actual filter pad.
Okay. So then that gets into a whole other category, which is electronic air cleaners. And you can go pretty deep down that hole if you want. Some people love them. Some people think they're, a bunch of stuff. I mean, I think there's something to them. So describe how that works, Brendan, because you probably sell these and have more experience with these than I do.
We do Air Ranger, but they're all basically the same design. So it's a metal cage basically that houses a fiberglass type filter that's really it's not as dense as a pleated filter, and it wires directly into the 24 volts on the system, and it produces a static charge on the filter that collects the dust as it passes through it.
And so it gets back into like charging particles and opposites attracting, and it kind of gets into the whole category of air cleaners too, where it's like we're going to change the polarity of these particles and make them stick to something. So that's, feel free to fall down that hole all y'all want, but that's a whole other category. That should be a class on its own, is just air cleaning. I will show you this though. It's pretty slick. Just found this. So your the recommended filter change. I wish I could pull this up larger. Let's see, control. So this is from April Air. So 1 inch filters begin with a high static, and then it's just going to get worse as it gets dirty. So they're saying a filter that starts with a 0.2, 1 inch filter. So this is as it gets dirtier. So after a month or two, your 1 inch MERV 13, they're saying that, some of those started as high as a 0.4. That's higher than our air conditioner coil. These down here, this MERV 8, 0.2 something. And then within just a few months, you're already you're at your max. And so they're saying, like, how long does it take for it to get to 0.5, which is where they're going to say is, the threshold. And then
I always heard
these.
Do what? For most. I had always heard that the MERV 8 was the preferred for like a 1 inch filter. Like it's not too restrictive and it's not too.
Yeah, I mean, people say, what should I go get? And I'm like, honestly, go get the middle of the road filter. Don't go get the greatest one. Like, get one of those. I've heard people call them a B&B filter. They'll catch bricks and birds or something, just like the biggest stuff that works its way through. That's pretty much all it's going to stop, but it's not going to kill your system. So as you can tell, I'm just not a huge fan, but you're going to see them everywhere. So that may be a good opportunity if you understand how this works and how it can affect your system. And it might be a real good time if you're there changing a motor to look at their filter system and be like, there's a possibility that, maybe look at their duct sizing too, but there's a possibility that if we were to upgrade this filter, we could prevent this from happening again, because, you're pulling a lot of static across this. You might want to go ahead and put in the new motor and then run a static pressure test. If you have a set of a set of, what's the word I'm looking for?
Manometer.
Yeah, well, yeah, I guess it'd be still a manometer. But yeah, you have something to read static pressure across that. Say, look, man, here's where this is at. This is hard on your motor. This is causing your motor to draw more amps than it should. And over a long period of time, that's going to cause this motor to fail quicker. So we could upgrade you to a MERV, whatever, get a better filter that's so much easier on your system. So like, look at this one. This is a 30 by 25 by 4 MERV 16. So that MERV rating is like, the higher the number, the more it's going to catch. I don't know what it stands for. I can't remember. But notice this one's huge, 30 by 25 by 4. So this is probably one of those where they've expanded that out and brought it back in. So they've spread the filter out, put a really big filter in, and let air just work its way through it. And it's the lowest one of all of them. And it's the highest MERV rating. So interesting. All right. So another thing within that, there are some different ratings within Aprilaire or any of these other filters, these 4-inch pleated filters. So like they make a 210, which is their standard. It's their MERV 11, I think. 213 is a MERV 13. That's what they call allergen rated. And then they make one above that. I think it's like a 16 series, and it's supposed to be like asthma rated. So it's supposed to catch like, just tighter particles. But obviously the more aggressive your filter, the quicker it's going to fill up because it's catching more stuff. So the change out time on these are a little shorter. But once again, you can see the 1-inch MERV 8, it's going through the roof. They also make a carbon filter. So if you ever run into a place that has a lot of odors, carbon is good at removing odors. I have had to do this in one time whenever they had a bad odor issue in the house, and I sold them one of these, and I sold them an air cleaner and the whole thing, or a purifier. And I was like, hey, since you got this bad odor, why don't I put you in a carbon filter the first time and clean this place up, and then we can just go back to the regulars. And that was what we did. It has a shorter change out period, but it's expensive, but it does do a good job. So if you had a place that was like a restaurant, you could upgrade them and put in a carbon filter, change it every 2 or 3 months, but it should, cut down on some odors. So just every application is a little different, but just know all that stuff is out there. All right. So I say all that to say that your filter selection is going to be a big deal. And so I'm going to go back to the Aprilaire, and we're going to use that number. So we want to keep this total number as low as we can. I mean, that's what we want to do. You'll also notice in Blackboard, get rid of this little thing. I also linked another coil. Let me pull this up. So if you're using an air handler instead of an air conditioner, or instead of a furnace with an AC coil, I don't think most of your manuals are going to come with the specs on the coil. So you're going to have to look up. I had to do a little digging, and I had to actually find the model number of the coil that came with the air handler that I was going to use, and then look up info on that coil. Now, if you have the brand new stuff, you have brand new everything out of the box, and you have all that there, you'll probably have manuals with that, and it may be included in that manual pack. But if not, I had to go and actually dig into the air handler manual to find the model number of the coil, and then look up the coil specs. And so when I do that, it gives me this. So this is an uncased coil. This goes, inside the air handler, just like what we deal with in class, or what we have in the classroom. And you can go down through here and you can find all the information on it, piston size and all that stuff. Condensing unit matchup, and then I'm looking for airflow specs. Dimensions, surface area. Let's see here. Pressure drop. Okay, so right here, static pressure drop through a wet coil. Depending on your case coil size, so let's say it's a 17-inch filter or 17-inch coil, and it is an upflow. And then here's 1100 right here. 0.1. Do what?
The cool. Is this for the house that we're using, or are we just using this?
This is for the house. Well, I'm just using this as an example. If you were using an air handler instead of a furnace, so we're not using an air handler.
I meant for the longhouse. You said it was an upflow. I thought, and our unit was in the crawl, correct?
It is, but it would still be going up. It's not a downflow. Like we don't have it.
Just a horizontal drain fan.
Yeah, it's horizontal, but yeah, it's still going out the top.
Okay.
So it looks like from that, you're going to have about a 0.1 through this. So not nearly the pressure drop that we had on the other. So just a little information on that. It's a little bit more work to find that information, but it is there. So just if you had to do that, you could find it. You just have to find the coil. And it might be in some of the manuals. I just couldn't find it in the Rube manuals for the air handler. I had to go this route. So that's that. So we're not using that number. I'm just saying if you had to, that's what you could do. All right. So the other things that are in here, if you have them, we don't have an electron or a hot water coil, so we're not using it. Electric resistance heating coil. I think there's kind of a basic number, but we don't have we have a furnace. We don't have electric heat. But I think that it's in your manual J somewhere, or manual D, but I would have to look it up. I didn't look it up because we're not using it. But your resistance heaters do have a little bit of a value. So I think it's like 0.03 or something. It's pretty small. But they do have a little bit of resistance. So you calculate that. Heat exchanger. All right. So this would be in your furnace. I did not look this up. Your furnace heat exchanger will have resistance to airflow. And so I'm going to have to try to see if I can find this real quick because I forgot to look that up. I got too many tabs open as usual.
So on this worksheet, what filter are we selecting for this?
So we're going to use the April air. So we're going to use that 0.08.
I need to look into putting one of those things on the package unit that I've got.
Good luck.
Really?
Well, it depends on how it's set up, but it's not going to be as easy on a package unit. Now, they do make them now where you can put them in the floor. You can get a little filter rack that goes down in your floor, and they've got some that go up in the ceiling if you have a drop down, but you have to have the depth to do it. So, it takes some changing.
That 0.08, is that on the high or mid efficiency filter? I had some audio issues.
Yes, it's on the high. Yeah, we're not using a low efficiency filter, so scratch that. We're just using 0.08.
Gotcha.
So if I go to my table here, wherever that's at, my friction rate here, we don't have resistance heater. We don't have this. We don't have that. Heat exchanger we haven't found yet. Low efficiency filter we're not using. High efficiency filter we're using 0.08. Electronic filter we're not using, but if, like Brennan said, if you were using an Air Ranger or some, April Air makes some really big, big wide air cleaners, electronic filters. So if you had that, you need to calculate that. Humidifier we don't have, but if you did, you could find that info. Supply outlet and return grill. So this is going to be like what type of vents that we're using. So they use 0.03 and 0.03. Let's use that for right now. And if we have time, we may get into where they got those numbers. But all that's in your manual J or your manual D when you start looking through the specifics of like different different vents and different returns and different runs. Everything has a static pressure loss across it. I think, though, that you could actually look this up from the manufacturer. So if you were going to go to 2J Supply and buy all your registers, if you're just using a standard, 6x10 register or whatever, you could probably find the specs on that pretty easy online. But it seems like 0.03 tends to be just a standard number that a lot of these end up using. So balancing dampers, if we have dampers, you'd have to count those. We don't. Other devices, and then that's going to be your total. So the only thing we need to find is our heat exchanger. So I got to find that's a coil. There's a filter. Gotta open that up again, I guess. Let's see, 95 series. Here we go. All right, so I got to find the static pressure drop across the heat exchanger if I can. Okay, and here you also see your minimum external static and your maximum external static so it's listed as 0.8. So we're below that. We're at 0.5. So, but yeah, they're saying the most they want you to go is 0.8. I'm not seeing what I'm looking for. I'm gonna look through the book real quick and see if I can find another example. And if not, we may just have to skip that part because I don't want to take forever on it. But well, anyway, I'd have to find it somewhere. I'm not having any luck finding it right off, but I forgot about that. Or would it be? No, it's not this.
I know this is kind of a random question, but could you use your amp clamp on the blower motor and test and see how these different filters are actually costing a customer money?
Yeah, I mean you could, for sure. Yeah, if you load that sucker up with a dirty 1-inch pleated filter, it's definitely going to impact your performance. Plus, it's going to impact your motor longevity. All right, so I'm going to skip that part right now. I'm just going to move on. So we've got this. So add these up. What we come up with? 0.38 and 0.14. Is that right? Yeah, 0.14. And then 0.38. So 0.62. All right. I'm doing this top of my head. That ain't right, is it? .38 plus 0.08 plus 0.03 plus 0.03. 0.52.
0.52, yeah.
Okay. Okay. Now, available static pressure, and this is right from this chart. So this is a pretty neat little document here. It lets you fill it all in. It doesn't calculate it for you, but it does let you enter it in. Makes it look neater. So available static pressure equals external static pressure minus CPL, or what they're calling DPL, which is component pressure loss or device pressure losses. So we know our device pressure losses is 0.52. We also know that our total external static pressure, let's see, we may have to, where did we get that at?
That was just 0.5, wasn't it?
Yeah, it was. And I'm trying to see if I messed up by picking 0.5. They have 0.67 in this example, but I'm trying to see where they got that at. 0.67, 0.67. You all got your manual D book. See if you can help me find out where they got that number at. 0.36 in this one. Like I said, guys, I'm learning this right along with you, so don't feel bad if you're a little confused, but let me pull up that.
Point one, the 0.1 rule's looking more and more.
Oh, it looks great. Yeah, it looks amazing. Let's see if I can find out where he got that at. Now I use that, so. Okay, so this says a system with an ESP of 0.5 inches of water column has the following device pressure losses. Da, 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 da. So he runs through that. What is the available static in the duct? So in this case, I would actually have to go to a higher external static pressure. Let's see, let me go back and check something real quick. I may have to speed up my blower to get it through. Let's see, what am I looking for? Oh yeah, this thing. So it looks like that refrigerant coil is a lot of our issue. So the fact that we need 1,000 CFMs is partly where we're picking up our problem. Because if we could keep that at the standard 800, but I mean, if that's your design, that's your design. So what else could we do?
You could take the static.
Do what?
You could take the static to 0.6, external static to 0.6, and then set the blower to high.
Okay.
And it would work.
So let me pull that blower chart back up. So he's saying if I turn it to high, that's one option. The other option would be, let's see. Let's CFM air delivery. Okay, so CFM air delivery, 60,000. If I turn it to high, I can get 1147 at a 0.6.
Or at 70, at 0.7, you get a 0.62 at high.
Yeah, you're getting pretty high on the point. You know, once you get up that high, they say they want a max of 0.8. But yeah, you can stay between. Let's see. If I do a 0.6, it gives me 942 on medium high. Or if I go to high speed, it gives me 1147. So we're saying we need a 10. So you're at a 0.7. If you do high speed, it's going to increase my static pressure, obviously, because you're moving more air. But I can move 1062 through it at a 0.7 static. So I could use that as my total available because I got more available because I'm moving more air, obviously, right? So I could enter that in. Let's see what that comes. Let's see what that gives us. All right. So back to our little sheet. So let's say 0.7. And I feel like there's probably a more precise way to get this number because in this book, they're saying like 0.67. I don't know where they got that number at. It must be something. There may be a more specific way in certain manufacturers, but I'm not seeing it on ours. All right, so just for argument's sake, we're going to use this number. It's not like any of y'all are going to do this in the next 2 or 3 years anyway, probably. So we're just going to get through this. What do you think?
Sounds good.
All right, cool.
0.18.
0.18 inches of water column, available static pressure. All right. So then I'm going to use that number down here. So now I got to find my total effective length. Now, let me show you something. I'm going to pull this over here. So I hadn't used this, and I hadn't even pulled it up till today because I just thought, oh, I don't know. Seems like it's kind of confusing. I pulled up the Manual D. I think this is your Manual D speed sheet through ACA. Is anybody fooled with this at all?
No.
It's actually pretty slick. So I had kind of wrote it off, and I just thought, oh, I'm not going to fool with it. It's actually pretty neat. So this will help you find effective length, friction rate, and potentially duct sizing. But I'm not going to, maybe, I don't know how far I'll go into that, but the effective length is pretty handy. So you can enter in up to 4 rooms, and you can basically say, like, what are my longest potential runs? All right, so I'm going to pull up my floor plan. So here's my floor plan. Everybody see this? Anybody see this? I don't need everybody. I just need one.
Yes.
Good. Okay.
Yeah.
All right. So my laundry room, my rooms at the end are most likely going to be my longest runs, but not necessarily. So what all things are going to impact what we call total effective length? It's going to be all the components that I use. So not only the length of actual duct, but the length of the equivalent length of like all my fittings. So if we're doing this as a metal duct system, and we're going to say, all right, I'm going to come out of this dining room, for example, and I'm going to go over, and then I'm going to put an elbow in. And then I'm going to come here, and then I got to go up through the floor. So I've got to put an elbow up and then put a straight boot on it or whatever. All right. So let's just use this one as our first example. So the length of the pipe, the length of the duct run, starting at the furnace, is 1, 2, 3, 4, 5, 6 pieces. And then I'm going to come probably off of this end by about 2 feet. So I'm not going to count this 2 feet in the middle. So I'm just going to say 6 pieces at 4 feet apiece. So it's 24 feet. All right. So I go back to this speed sheet and I enter in 24, trunk length 24, dining room. So 24. Run out length. All right. So how long is the straight runs? 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, let's say. So let's say 12 feet. All right, so I'm just counting the length of the duct right now. I'm not counting any fittings or nothing like that. Now, this gets into your fittings. So if you go to your Manual D and you go to like back toward the back half, let's say like page 156. That's a good example. 156, 157. If you have your book, you can turn there. If not, I'm going to be able to pull it up from this. So this is what's pretty neat about this. It references all the stuff in Manual D. And so if I click on Group 1, it's going to say how many Group 1. So if you go to your Manual D and you go to Group 1, that's your air handler takeoff stuff. So what's coming directly out of the air handler. So I'm going to pull this up and you're going to see exactly here we go. Can y'all see that? Yes. No, you can. All right, so this is straight out of Manual D. On page 147, Group 1. So this is like what type of takeoffs do I have coming out of this? What type of plenum system do I have? And so coming directly off the furnace, let's say I want to do just a square rectangular plenum coming off, and plenum is just a word for the thing that comes off the top of it. Coming off the top of the furnace, air handler. All right, then I've got a couple of options. So I could say I'm going to go straight to a rectangular or round pipe, no transition. Or I can put this little transition that's on this right side on this 1B fitting, a little more work. But if I'm trying to save length, it may be worth it to actually transition this. So anytime you can kind of make the air work its way in versus just abruptly having to force its way through, it reduces your equivalent length quite a bit. And so what this is saying is each of these configurations or each of these fittings has a total equivalent length, which means it's essentially saying this fitting or this configuration is the same as 35 feet of straight pipe. The friction that would do. So think back to the whole like example that we've talked about in the past of like you're trying to breathe through a straw. The longer the straw is, the harder it's going to be to move air, even though the diameter doesn't change, right? So in order to move air longer, sometimes you have to upsize the diameter to keep your friction down. So your equivalent length is saying like this particular configuration, this no transition setup, which is pretty common, has an equivalent length of 35 feet of pipe. But if I transitioned it, I could get it down to 10. So I'm just going to say I'm going to use the generic one, and let's just see what happens. So I'm going to use a 1A EL35, and that's straight out of my book. So my equivalent length is 35. You go to this effective length, and I could say I'm going to use a 1A. Oh, sorry. 1A equivalent length is 35. All right, next one, group 2. So if you go through your manual D book, there's a lot of different configurations on group 1. Skip through that. The next one is group 2, branch takeoff fittings at the supply trunk. So click on that. You're going to see the same thing that's in your manual D book. These are the type of fittings. So these are common what we would call takeoffs. Let's see. So like down here, refer to fittings. So this is just a round takeoff. This is pretty common. This is what I use a lot of times. A little different. This is one that you'd actually screw in and it goes into like duckboard, but a round fitting, straight to round. Refer to 2A or 2C. So 2A and 2C. I don't really know the difference right off. Can't tell. Seems like there's a huge difference, but oh, there's a damper in it maybe. Okay, and then fitting 2D would be like a rectangular. So instead of running a round trunk, you're going to run, or a round branch, maybe you're going to run another piece of duct or something. And then you can also use fittings like this, fitting 2E, which is a transitioned to round. And so it reduces your equivalent length quite a bit. So let's see what that looks like. 2E looks like 25 compared to 35. So you're reducing it by 10. Now this says number of downstream branches to the end of the trunk or the number of downstream branches to a trunk reducer. So with ours, we have trunk reducers. We reduced every time we took one off. So there's really not going to be any downstream branches before those reducers in most cases. Now, if, for example, like this one right here, let's say in this one, there was another one that came out right there, then I would have to go to a different column and I would have to say, all right, I'm going to use, where's that at? This. I'm going to use this column because there's one more downstream of it before it reduces. So if not, I'm just going to use this first column. There's none. And I'm going to say that round takeoff has an equivalent length of 35 feet. All right, so I'm going to use a 2A. Go to my equivalent length. What did I say, 35 or 30? 35. Group 3, if you look through your book, Group 3 covers reducing trunk takeoff fittings. We don't have any of these. These are kind of odd, in my opinion, but I've never seen one of those, so we're not using those. Group 4 is supply, air boot, and stack head fittings. So this is like, these are really common. So this is your takeoffs and these are your boots. So by boots, I mean, this is what's going to blow up through the floor, ceiling, wall, whatever your design is, how you're going to deliver air to the space. So there's a lot of different configurations here, and you can get pretty creative with these. But for my experience, what I've used in the past, we end up using a lot of 4Q, which is this, what we call a center end or an end outlet boot, which would be like if you're running down a duct and then you're going to come straight up that way with the horizontal or with the length straight ahead out the throat of it, then that one has an equivalent length of 50. This is what I would call a straight boot, this 4R, and it has an equivalent length of 20, but I'm probably going to have to, in some cases have to use an elbow to get up to that. So you have to factor that in as well. And then the others are 90s. So a 90 boot looks like, where's it at? Right here, 4G. So this 4G has an EL of 80, so it's pretty aggressive. It's taking up 80 feet worth. So probably not the best thing to use, but you're going to see them a lot. So it has an equivalent length of 80 feet. So if I have one that has this EL 20, if I have a straight boot, and then I have another one that has an 80, even if the run itself is longer, on this one down here, I may end up having a shorter equivalent length on the run because of the boots and the elbows that I have to use. All right, so let's go back to our drawing. So this one, we're going to use a straight takeoff. We're going to use one elbow, which we haven't factored in, and then we're going to use another elbow to get up because we're going to come straight in with a straight boot. So most of the time, your joists are running like this. They're running this way. Boom, 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 boom. Your floor joist. So you'd have to know like how to get that duct up in there. So I've got to be able to get this up inside of that joist cavity from underneath. So in order to do that, I'm gonna have to run a straight boot, an elbow, and a takeoff on this one. So this is my dining room. I got to go to back to this. So effective length. So on this one, I'm using a straight. So it's an EL of 20, 4R. EL of 20. And you don't have to do every single run in the house. You're just going to pick the ones that you know are probably your longest, and then you're going to find the length of your longest. This would be your elbows and offsets. So like you might use these 4 or 5 piece adjustable elbows. These are pretty common. So let's say we're going to use 2 of those, and it's turned as aggressive as it can. It's 90 degree, or close to 90 degree. So I'm going to use this 30 equivalent length for each one of those. So I got 2 of those, and those are, well, crap about that. This one. So we'll say they're 30. Yeah, I don't know the group number. All right, 9. Supplied trunk fittings. Nothing crazy there. Return. All right, so you also got to, let's see. Group 11 is flexible duct junction boxes, radius pins. So this is if you're using flex instead of metal, then you could say, okay, now what is the, how many bends do you have in it? It's going to be the same as if you had an elbow. You got to calculate that in. So just because you're running flex, you're not putting physical elbows in. You still got to calculate, your turns. And then 12 transitions. So our transitions are in our duct work, we're going to say they're more like this. So I'm going to say, I don't know exactly what all that means. I'm not going to put anything for that. Okay, so that gives this supply a total length of 156. This one over here, I ran it earlier. This was I did it before y'all got on. This is, actually, we had 2 elbows on this one, so I got to count both of those. All right, so this one is your laundry room. 1 elbow, 2 elbows into a center in boot. So let's see if that one does how that one does. So I've got a end outlet boot right here, like this one, 4Q, EL of 50. So different boot, different length, and then I have 2 elbows, so 60 feet. So that's my longest run so far, 211. So it's calculating my longest one. And then let's say I have one more. Let's say I want to run one of these over here, one of these simpler ones. So let's do the one at the bathroom because it's going to have an elbow in it. And it's going to have 2 elbows. It's all the way at the other end. 1, 2, 3, 4, 5, 6, 7. All right, so 7 feet of duct. There's 7 pieces of duct at 4 feet apiece. Length 28. My run isn't nearly as long. So let's say it's 1, 2 by 4, let's say. All right, so 10 or 6 feet. Really short run, but it's got to go a long way to get there. The takeoff, let's say that this is exactly the same as that last one. So this is how it comes off the duct. Let's say it's 35 feet, just like the last one. And same here, 35, just a round takeoff. None of that. All right, down here. And I'm going to use a straight boot and 2 elbows. So this one's got an EL of 20. And this one has 2 elbows at 30 feet apiece. So it's still not my longest run. So my longest run is 211. The other ones aren't going to be unless there's something weird going on with them, most likely, because they don't have as much duct. But you could still run those if you wanted to. But this is just kind of like it lets you pick 4, and you could clear them out and run some others. If you see, like here, this one isn't my longest one, so I could just delete that and can't delete it. But I could go in and change it for another one and just say, okay, let's try the hallway or whatever. All right, the return, you do the same thing. I'm not going to spend a ton of time on that. I'm just going to quick and dirty say like, okay, same setup. Say it has a EL of 40. So let's just say we're going to use one big central return. It comes straight in, 6C, comes in round. I don't know. I'm just going to pick something, 75. I'm moving pretty quick at this point because I know everybody's done.
I was going to say, use panning in this situation.
You can. So panning is right here. So this was something Chris asked me the other day that he was watching online, and he said, hey, I found out that you can actually, that people use floor joists and they run their returns through the floor joist, and all they do is put some metal or something underneath of it, and they use that as a duct. You can do that. That's called panning a joist. You can do that on return. You can't do it on supply unless you insulate that supply or insulate that duct. It's like in dire straits, the only reason you do that. But return, it's done all the time. So like, here's an example of it right here. Stud space, 800 CFM, whatever, double stud. So you could say, well, what is the dimensions of this cavity, this floor cavity or whatever? And then you can pan that and pull a return through that, use it like a duct. So if they're doing that, let's just say we're doing that. So it's a 7E. And let's say I want to move 800 CFM through that one. So let's say this is going to be a main central return, and then maybe I have a couple others coming off. But just for our argument's sake right now, let's just say we're going to pull 800 of it through that big floor return, one big floor return. 110 equivalent length. All right, so I'm going to put that in. Or effective length. All right. Group 8 is your elbows. We don't have any elbows on this one because we're just running it straight into the duct. We don't have anything crazy here. Just straight into the duct. No flex. All right. Now, let's say that, so that's one. That's our main. Let's say we got one big hallway return. And then let's say over here in this bedroom, just for argument's sake, we have Oh, wait, I got to run trunk length. So let's say that one's not very long at all. Let's say it's 10 feet long, and the run out is another 10 feet. So that one's pretty close to the center. If you look at if it's going to go here in the hallway, it's going to be real close to your air handler. All right, now let's say back here in this bedroom, I'm going to pull a return from back here. So I'm going to go 1, 2, 3, 4 pieces. No, wait, 1, 2, 3, maybe 4 pieces. And then I'm going to pull this return out of the end. All right, so this one's going to use flex, let's say. So it's going to be fairly small. So 4 pieces is 16 feet. And then let's say we go 1, 2, 3, let's say 4 feet. So let's say 20 feet total of duct. So 20 feet, there's 16 and 4. And then it's going to have flex. It's going to run to the same type of main return. So I'm going to keep that the same. 40 feet. Group 6 is my branches. So let's say I'm using a 6C. And I'm just going to pick a number because you'd have to kind of dig into this a little bit. Let's just say that it is 75. And then group 7, we don't have because we're not panning on this one. Group 8, we do have. So let's say we run this one in flex. So no metal, just flex. All right, so let's say we have one bend. It's 90 degrees. 90-degree bend. Let's see, equivalent length. I don't know the velocity right offhand, so I'm not gonna. Let's just go back to our metal. I'd have to look at that. Yeah, I don't want to fool with that right now. All right, so let's just go back to this. Use our 90 at 30 feet, just like we did before. So 190 at 30 feet. And our boots. Let's see. Where's our boots? Yep. Doesn't give me the option for a boot. All right, so basically you can see my process though, what I'm doing. So that one is the big one is still the longest because I'm moving so much air through it. So 245, my total equivalent length is going to be the sum of these two. Friction rate, external static pressure, 0.6, or what do we say, 0.7. CFM from tables, so we're going to move, let's just say 1,000 and 1,000 for argument's sake. And we're going to run the fan on high. Let's say we're in the wintertime, we're going to run 800 because we need a little less. So we're running on medium. I could adjust that if I wanted. Component losses, direct expansion, coil, 0.38, wasn't it? Something like that.
Yes.
And then this was 0.03. So this is the same thing we're doing, but it's calculated for you, which is pretty slick. UV lights, that's in there. What was the other thing? Filter.
0.08 on the efficiency filter.
0.08. All right, so there you go. It's calculating all that. It's giving me my available static. My total equivalent length is 456 feet. My friction rate is 0.04. There's the number we've been looking for all this stinking time. So the 0.1 is what we were kind of saying it was going to be. And then in this case, we're going to say it's 0.04. So let me just look at one example of that and see how that changes things. Cut your duct slide.
Yep.
Pull out your duct slide, and let's say we're going to move 1,000 CFM at 0.1. All right, so I'm up to the top right here.
Yeah.
I'm going to go to 0.1, and I'm going to look at my round duct diameter to move 1,000 CFM, and then my equivalent rectangular. So 0.1 at 1,000 is about 14-inch duct.
Yeah.
And it takes what size rectangular? James, what's it take? You got yours?
10 by 16.
10 by 16 or 8 by
about 20.
8 by about 20 or 22. Yeah. All right. Now slide your duct slide to 0.04 at 1,000. How big round does it need to be?
17 inch.
17 inch and 8 by
12 or 20 by 12. Right on the dot.
12 by 20, 10 by 25, or 8 by 33. Same system. Now you see why most of these homes, the ductwork is undersized. Because if you're not taking a good look at what your actual friction rate is, and you're just assuming that it's 0.1,
that's
now
huge.
everything is you're trying to force everything through a tighter hole, which means your motor's drawing more amps over time. Then they go in and they say, okay, let's say you design it for 0.1, so you're already undersized. And let's say that you size it for a medium, like just a standard grade filter. So just you go out and you buy one of those B&B filters off the shelf, and because I don't want it to be too aggressive. And then they get the big bright idea that they're going to go buy one of those awesome filtreats, and they stick that in the thing. Now what?
Yeah. Now it's not.
Now they've changed everything, right? Then you throw a little dirt on the coil. All right. Then you throw a little dirt in the ductwork. Then they go into their bedroom and they close some of their vents off because this one blows too hard, or they put a rug over that one or whatever, right? Any changes to that system are going to cause more issues. But from a design, like from the beginning, you're already undersized. And so especially with like these ECM motors, those ECMs will run. And so like, remember back in your electricity class, we talked about the difference between constant volume and constant velocity. So a constant volume motor will try to move the same amount of air no matter how hard it has to push it. And so if you have a dirty filter on a variable speed motor, it's going to run like crazy to try to push that much air. And so as it pushes that air, it'll get it if it can at all. If it's there to do it, it'll do it. It may have to run its guts out to do it, but it'll push it. And so it'll run like a freight train. It'll blow like crazy to try to blow through those restrictions. So variable speed motors are good because they will kind of make up for our shortcomings, but they're bad because they'll make up for our shortcomings. And so people will put in these undersized systems. They'll put a variable speed motor in there, and they'll be like, it'll push it. It doesn't matter. But then the problem is 4 years down the road, that $1,500 motor's shot. And so if you start having ECMs, especially ECMs, variable speed motors, electronically commutated motors that are failing, look at airflow, look at duct size, look at filter design, look at coil restrictions, look at all that stuff. Because if they're constantly blowing through motors, or even they go through one or two, that's a problem. If they go through an ECM motor in 4 years, that's probably a problem because they're running this thing too hot, and that thing eventually just melts those windings or whatever, overheats, or it starts tripping itself out constantly until it fries the board or whatever. So like it may do it, it may push it, but it'd be noisy. That system's going to be really noisy. It's going to blow hard, but it has to do that to move enough air through the straw that you gave it to blow it through. Does that make sense?
Yeah.
All right. So normally in this class, we take a visit, but we're not going to be able to do it this time. But just to give you a realistic example of this, there is a guy in Clay City. Some of y'all may know him. His name is Ricky Wasson. Ricky runs a music store up there, Rick's Music World, up on between Clay City and Stanton. And his son actually went through my program. And a few years ago, we were talking, and I was just, had him go home and tell me what kind of system they had or whatever. And so he goes and says, well, at my house, I have this, but at the shop, we have this other thing. And so he didn't think it was that big of a deal. And I was like, man, this is kind of crazy when he got to talking about it. So we went out and visited this. They got a recording studio back in the back. And it's legit. Like, it's a really nice setup. And he built it from scratch. He didn't know anything about heat and air, but he knew about recording studios because he's been in Nashville for years. And so he built this studio the way that he thought that most of those in Nashville should be built. And so each room has its own ventilation and its own thermostat. And so he put in a zone panel for each little recording booth, because he said most of the ones in Nashville that he'd been in, there may be a vent, but if it is, it's just tied to a main stat. And so you'll see guys constantly just throwing the door open, get a little air in there or whatever. And their guitars are always going out of tune, and they have to take breaks all the time. And so he was like, if we could keep this room conditioned, we could record quicker, get in, get out, and move on. And so in theory, what he did, and it's amazing what he did, because I would have never thought this was possible. In class, the next time when we go through our little layout, we'll do branch sizes as we're going to kind of see how big of a run I need to move this much air through. And so if you look at your little thing here, let's say at a 0.04 static, I need to move 150 CFM. All right, what size round duct do I need to run that in?
8-inch.
About 8.
About 8-inch. All right, so back to my picture here. Right here. This bedroom down here has 128 that it needs. When you're sizing your runs, that's all you're doing, is you're just matching up your friction rate with how much air you need to move. So 128 at 0.4 is what?
7.5.
About 7.5. So I would go bigger. If you're in between, I'd go up. So I would run maybe an 8-inch there. Now back to your 0.1. So go to 0.1 and move 128 CFM.
About 6.5 in the round up.
Yeah, and I'll go ahead and tell you, most people are going to put a 6-inch in there, just because it's what we do. And so you go to every bedroom, you give every bedroom a 6-inch, and I'm guilty of it too. Every bedroom gets a 6-inch, unless it's a big bedroom and it gets an 8. And bathroom, so the bathroom gets 27 CFMs at 0.4. So that's really small. I won't even go that far, but let's say it's 30. So that's like a 4.5-inch duct. Most of your bathrooms are probably going to have a 5-inch duct in them. You don't need a lot. The problem you'll see with bathrooms is that people that just use 6s on everything, and 6 is kind of like the go-to. They'll put a 6-inch in a bathroom and it freezes you to death. It blows all the time. It freezes you to death. And so people end up shutting them off because they get out of the shower and they got this cold air blowing on them. So they shut them off. So then they don't get anything.
I said, woo.
Yeah, exactly. Yeah, woo. Yeah, shut that thing down. So let's see, where was I going with that? All right, so in his example, he said this booth, he done a bunch of research on his own. And so this booth may be 8 feet square. It's not very big at all. All right, so, if I'm sizing just by rough sizing, a 5-inch duct should be plenty. 50 CFM of air or something. All right, now he's saying, okay, 50 CFM of air, so many BTUs. I got a dude in there playing a guitar. He's sweating. He's big, whatever. So maybe give him, 100 CFM of air. All right, so go to 100 at 0.1, where most people would go, and they would say he needs a 6-inch duct. Here's what he did. And most rules will say as straight and as short as possible, because you don't want any bends that you don't need. You just want to run it straight there. Keep your equivalent length down. Here's what he did. He goes in this room, and it blows my mind that he even knew to do this. he goes in this room and he goes to each of these rooms and he puts a 10 or a 12-inch supply and a 10 or a 12-inch return in each of these recording studio rooms, in each of these booths. And then he coils the duct 100 feet like a snake in the attic, and then runs it all to his main system where he's got dampers controlling each one of them. Each booth is ran off of a thermostat. Why did he do that?
To increase his run?
He increased his run. He's got 100 feet per run at 10 or 12-inch flex. Just coil like a snake up in the attic. He said it's the awfulest mess you ever seen. Why did he do that?
That would increase his velocity, wouldn't it?
No. So imagine if you're blowing through a straw and you have a little small straw, you blow as hard as you can, or through a piston, even like a little bitty hole. Your cheeks are going to puff out, right? That's static pressure. That's back pressure.
Oh, it makes it quieter, doesn't it?
Yes. So once it gets through there, you're going to have a lot of velocity, right? Noisy, loud. You're moving enough air, but at the harm of noise, right? You're losing quietness. So most HVAC systems say, well, you have to move so much air to actually be able to move it through the building. Like you have to have so much velocity. And I agree with that. In his case, though, these rooms were so small that it didn't take much air to do them. But if he ran a 6-inch flex, he couldn't record, because when he turned it on and he turned those mics hot, everything got hot. He picked it up. I mean, he said even now, like my furnace, if it kicks from low to high, I can't record on high, even at that, because I can pick up the noise. And so he has to make sure it's in low stage. He's got a little switch on his furnace that he flips it so it won't go out of low stage. He's a pretty slick guy. He worked with a contractor and they designed this themselves. But so he's got this humongous flex, run all these feet to just take up space so that he delivers the right amount of air, but it delivers it really, really slow and really, really quiet. And so I never thought about it, but like I always thought you're tied to this thing and you say, well, in order to move 100 CFM, I have to have 6-inch duct. Now, could I move? So look at, take your slide rule to 10-inch. Go to 10-inch diameter, round in the middle. Okay, how much at 0.1 would a 10-inch flex move?
425.
Or a 10-inch round, yeah. At 0.1. 400 and about 415, 420 CFM. Yeah. Now, what if I go down to a 0.04? What will it move?
250.
Right around 250. All right. Now, what if I wanted to move 120 CFM through that vent? Could I do it?
Yeah.
What's my static at that point?
It is way down there, like 0.025. 0.0125.
0.01, yeah, about 0.01. Mm-hmm. So by reducing his static pressure, he reduces his velocity, which reduces his noise. So you can move. So I think we think of it like, in order to move a gallon of water, I have to have a 1-gallon bucket. But I can move a gallon of water in a 5-gallon bucket, and I can put a gallon of water in a tanker truck. Like they'll all hold it. As long as I have enough, I can always go bigger, but it will be at the expense of velocity, at the expense of speed of air. So I have to have so much speed to move it in most cases. But in his case, he kind of took that whole thing and said, well, hey, what if I slow it down? I can still deliver the right amount of airflow, and I deliver it slow enough that my mics don't pick it up. Pretty brilliant. Pretty genius. So with that being said, hopefully, I know this is a lot, but hopefully this hasn't completely bombarded you. And you kind of see the process, at least in theory. I know there's a lot of specs, things that I don't understand, that you don't understand, and you can see how you can really, really fall down this hole. But it's telling me I got 5 minutes left on here, so that's good. We're getting ready to jump off here anyway. But anybody have any quick questions before we do?
Yeah, on that guy's system, you said each of those sound booths had a thermostat,
Yes.
but he only had one system.
Yep. He has his own system. So each room has a damper on its supply.
Oh,
And
if it's
so
close
when that
enough.
room calls for it, it opens that damper up and lets that room have air, but the one next to it may not need it.
They're such a nightmare.
Yeah, they are a nightmare, but it's pretty slick. I'd love to be able to go. We usually go every year, but this year I didn't even ask. I'm sure he wouldn't care, but still, I just didn't. So here's what we're going to do next time. The weather looks good from what I can tell. I looked ahead to next week, and as long as nothing changes, it looks like there's like a 20% chance of rain. I want to go out back in that space outside. I'm going to get some chalk, and we're going to draw this house, this longhouse. Everybody get a room, whatever. We're going to draw it out as best we can with chalk. It'll rain, rain will take it away, so no big deal. So we're going to design this house, and we're going to walk the floor plan ourselves, and we're going to lay this out in real time. So if I was going into this house, walking into a house that's just roughed in, no walls finished or anything, just under roof, that's usually when I'm going to be going in and doing my on-site. So we're going to simulate an on-site load and how you do that. So at this point, we know what our friction rate is because I know what equipment I'm going to use. Now, those kind of, it goes hand in hand. You got to know your heat load, blah, blah, blah. So we're going to assume that we know everything we know up to this point, and then we're just going to walk through the house and say, all right, 4 feet, how many come out of this run? All right, what size does our duct need to be? That way you'll get to see it in practice a little bit anyway. So bring your slide rules. The last thing I'm going to have you to do, you can go ahead and start working on it. I want you to size this duct system, the same exact one that I gave you last time. So I'm actually going to just copy this and send it to you. I'm going to save this again, and I'm going to upload this at the end. This will be your final duct project. So you're just going to size this duct based on a 0.04. So see how that changes based on the one that I gave you last time, which was at a 0.1.
Can we change the 10 and the 8, or do you want us
Yeah,
to use 8?
You can change the 8 if you want. You could change it to 10-inch, but I wouldn't want it any taller than 10. Now your first piece could be 12 if you needed it to be, because it's going to be right off the top of the furnace. But just think, you're underneath the house, so you're going to be limited on space.
Okay.
So you could go 8-inch tall, or you could just go 10-inch tall and make it a little bit narrower. But that's kind of, and on the return, honestly, don't worry about the return in this case for now, because it's not laid out quite as handy. So I'm going to just delete that. I just want you to do supply. And then beside all these supplies, I want you to see if you can tell me what size each of these supply runs need to be. So like this one down here, the laundry room at 77, go to your slide rule. I got 2 minutes before it looks like it's going to kick me off. So at a 0.04, I need to move 77.
Okay. I got
so
you.
It looks like about a 6.5. A little less than 6.5. So you could probably do that with a 6 because it's closer to 6. I would round either way, but if it's very close to the middle, I'd go on up. But in that laundry room, I would think a 6-inch would be plenty.
Okay.
Do what?
On the supplies to the rooms, you want us to run round duct, correct?
Yes,
not
round duct. Now, the one thing I did want to say is flex. So if you wanted to run flex, this one has a wire helix flex duct equivalent.
And you can do it that way.
So you can do it that way. You can say, okay, at a 0.4 at the top, at 76 metal. Let's see, am I looking at that right?
0.4 or 0.04?
0.04, sorry. 6-inch duct. I'm looking at this round.
7-inch.
7-inch, how'd you get that?
I took the wire helix static pressure and lined it up with the volume CFM.
Oh yeah, I'm
So-
looking at it wrong. Okay, yes. So it's that use the bottom blue line instead of the top one,
Oh, okay.
and you line it up with the middle white column again. So if you're using flex, you can use that. The old duckulators that I used didn't have any sort of flex correction. It was all for metal, and everybody used it for flex. Another reason why we're undersized. So
Okay.
same way with duckboard. If you're using duckboard, it's down here on the bottom. So if you're using rectangular duct, that's here in the middle. And then if you're saying, yeah, but I'm going to use duckboard, you got to go down here and calculate it there. So
Okay.
same thing there. This is pretty slick because it does all that for you. The others, like I said before, what I used didn't have any corrections for duckboard, no corrections for flex. It was all metal, and nobody used it for metal. So
if I'm reading this right, a 0.1, so 1,000 CFM at a 0.1 for helix flex duct is a 16-inch diameter round.
probably, which that's, I mean, that's that's trying to move all of that unit through one. So that would be like a package unit. So a package unit, most of the time they have flex or metal that goes to them. And, they have a one big takeoff, and then it dumps it into a duct system, and then that duct system gets pressurized through that flex. So yeah, if you were trying to move 1,000 CFM at a 0.04, you're going to need 19-inch, so 20-inch round flex, which is humongous.
Yeah.
If you do it at 0.1,
16
round.
Yeah.
So it just gives you an idea of the difference. But yeah, if you go too big with your duct, I have run into this with one system that the duct was really oversized, was really big, and I couldn't move, and it moved it, but I didn't think I was going to be able to move enough air because it slowed everything down to the point that, like, they had an old PSC motor which would just move the right amount of air, and I put in a variable speed motor, and when you put in that variable speed motor, it'll only move a constant volume. And so it had this humongous duct, and the old system moved it because it had this PSC motor that just blew what it blew. And then I put in this variable speed motor, and it didn't have enough static pressure to actually load that motor up because it could move what it was supposed to move without turning very much. And so you'd go to the vents, and you wouldn't hardly feel much of anything. And I was like, oh gosh, this ain't going to work. But it actually worked really great. The guy was tickled to death with it. And he goes, man, it's so quiet. Like, I don't have to turn up the TV now. But I was worried about it because I was afraid it was too slow. So you do have to have enough air to move it. So that kind of gets back into, like, lower static rate, bigger duct, but you got to be careful about that because you can go, you can go too much. So I say most of them are undersized, but you can go too big, especially with ECM motors. And then you get that motor to where it won't move the air it's supposed to move, because all it's supposed to move is what you told it to move. And if it's got this big old space to do it, it'll move it, and it doesn't have to work very hard to do it. So watch that as well. But most of the time they end up undersized because of the 0.1. Whoa! All right. Any other questions?
Other than I definitely need a explanation of what you need us to do for our homework here.
Okay, so what you're going to do is I'm going to upload this new file with the ducts drawn on it and everything. You're going to tell me the new dimensions of your supply ductwork and the diameter of all your flex runs.
Do you say that's our final?
Your runs. And this is going to be your final duct design project, so to speak. And then, like I said, next week you can hand that in to me, or you can turn it in on here. Yeah, I just turned it on here. It's easier. Just turn it in on here, and then bring it with you next class. We can use that as a guide. It shouldn't take us long to walk through that, but I would kind of like to walk through it in real life. That way we get to see it. And then what I'm thinking about, I'll send you times to start. We may not start. If we can get everybody together, we may not start until the 10 o'clock block. Everybody come at 10, and then we'll go to lunch afterwards. I'd say I feel like we can run through this fairly quick since we've pretty much done all the work to it. And then we'll go grab some lunch or something. So, sound good to everybody?
Sounds good
to me.
be our last
Sounds
hurrah.
good.
Now, as far as ACR 200, those of you that have that class, when I see you again, the only thing we're going to do is we're going to charge that freezer up. So if you haven't already done so, just you should have your winter charge already calculated. We should have a rough idea of how we're going to charge the rest of it. So it shouldn't take that long. Basically just showing up and getting it to a clear sight glass, and then adding our winter charge. And then if you're in the Wednesday group, we'll recover what the Monday group put in, weigh out what they put in, and then we'll see if they're right. We'll do our own. So that's the plan.
Do we have anything for the 200 for tomorrow? We just kind of work on Blackboard, go through things.
No, yeah, just work through the Blackboard stuff. So I did put a module on there yesterday or the other day, Sunday maybe, about flammable refrigerants. And that's more just for your information because it's something that's coming down the pike. So if you have any interest in doing this at all, that would be something I'd want to check out. I'm not going to assign anything from it, but I think it's something you'd want to be aware of. So just check as much of that out as you can. There's some podcasts on there to listen to, and some videos and stuff, and some documents. So it's more informational than anything, but I thought it would be something we probably need to talk about. So
I know they've limited R22 to purchase of only 2 jugs now. So
really,
yep.
huh?
So it's R22 is getting ready to be gone.
Is that because of COVID?
No, I think.
Or is it just supply?
I think it's supply.
How much is it now?
I don't know the updated actual price, but it's took a hike.
400, better than 4.
What, for a jug?
For a jug?
It was $633.
What?
In
I ain't bought
Lexington,
none in a while.
$633 at Train.
Gee, last I bought was 3 something, and that ain't been that long ago.
$633.
It's going back to 800 again, like it was a few years ago. All right, so what'll happen is it'll get so expensive that eventually it won't be worth nothing because nobody will be able to afford to buy it. So it's like R12. R12 did that. It got to where it was like $1,500 a jug, and then now you probably couldn't give it away because everything's been retrofitted or changed out. So,
yep.
But there is some information on there about some possible replacements for 410A because they're already talking about in 2023, California's phasing it out already.
Really?
Yeah, they're going to
607A?
R32, I think, which is a flammable, mildly flammable refrigerant. But check it out. There's some info on that. If you're in that class, there's some info. You're not, but still, you might want to check it out still yet. But they're saying probably by 2035, I think, or 2032, they're thinking that a lot of others may start phasing it. Or maybe even be phased by then. But with 410, it was a 20-year process. Like they started it in 2000, and it didn't complete, or 22, I mean, and it didn't go away until 20. Well, it's still here, but it's on its way out now. But
yeah,
California's done said, according to what I've seen, and Daikin's done signed a thing. Daikin says that all their systems that are manufactured for, I don't know if it's certain countries, certain markets, or what, will be R290 or something. I was doing some research on that while I was looking at that, and I was like, wow.
Great propane.
Do what?
What is the refrigerant grade propane, like 607A?
No, that's 290.
Oh, that's 290.
Yeah, so that's what's used in most of the commercial stuff, your little small stuff. It's already there. One of the guys the other day, I don't think Jeff ain't on here, but Jeff sent me a picture of a fridge that he bought at Lowe's, and it said, "This refrigerator contains flammable refrigerant. Do not use a torch. Do not pierce it. Do not, whatever, to service it. Let a licensed person service it." But so it's already here. It's been here for a while, but we just haven't worked on it much. If you're not in that specific field.
So are we going to have to get licensing, you think, to handle these refrigerants as they become more common?
I mean, it still falls under your EPA, but you're responsible for any updates to your EPA certification that you'll get. So you wouldn't have to take the test again, but there's probably going to be some outside certifications that would, you could go through some trainings and probably get, but your EPA license should cover it. And actually, EPA don't give a hoot about propane because you just let it go. You don't even have to recover it. That's the whole point, is it's environmentally friendly.
Woohoo.
So like if you watch, there's a few videos online of people servicing like coolers with 290 in it, and they just open them up, blow it out, pump it down. Pull the vacuum on it and charge it back up.
Simple.
So there's no benefit in recovering any of it?
No, it's actually, well, they say there's a recovery machine, but most of them say don't, because they don't want any machine running that, like, it has to be a spark proof machine to where there's no way that machine could have a spark in it. And so with propane, they're just like, just let her rip, like take her outside, blow a fan or something across it just to disperse it. You're only talking about a few ounces, and then just get it out of there. The way most of those guys do is they take a little leak detector that's got a combustion leak detector on it. They set it over next to them, and they just start bleeding it out. And if that leak detector starts going off, they just stop for a second and then bleed it back out again until it's all gone.
Wow.
So listen, get on. Those of you that aren't in that class, like Brandon's not in that class, and Walt and some of you guys, if you're interested in that, HVAC school has some pretty good. They do some interviews with some people that do that for a living, and they talk about how they service it. And then you get on YouTube and do a lot of tinkering around with it. But it's coming in some form or fashion in the next. If you're going to do this before you retire, there'll be something. 410 will be gone, I would say, in the next 15 years.
Which is another reason to buy the digital gauges that can update to where they can update them with the.
Yeah, it's just it should be. It's probably already in ours. 290 is, I'd say. All right, guys. Thank you. And like I said, I'll try to upload this file. Only thing I want you to tell me is duct size and trunk size, or branch size. So trunk and branch sizing. That's all I'm looking for at this point. So we know our friction rate now. That was the big mystery that we had to solve. So now that we know that, we can get a pretty accurate sizing. So if you got any questions, stick around here for a second. I'm not going to be able to stay on long, but I will talk to you all later.
See you.
All right. See ya.
Yeah.